Fantastic. Thanks a lot, Cornel, and good afternoon, everyone. I will present today one of the pilot services that we've been setting up for SMHI and on behalf of the eShape project. And that has to do with a large-scale Earth observation-driven water service so that we can use it in order to address the local user and the market needs. I'm sure you all are aware of the fact that digitalization and Earth observations have evolved significantly the water sector. Here I'm presenting a number of applications that belong in the water sector where local users are operating. And the traditional approach is when somebody like a consultant is setting up water services for these applications. But the difficulty there is on the fact that if this needs is required to be applied in another domain, then a new service needs to be set up from scratch, and that requires a lot of technical foundation. So through a large-scale hydrological model, which is actually the foundation of a water service, one could tackle this type of requirements. At SMHI, we have been setting up hydrological models for the large scale, and by large scale, I mean for the entire country or for the entire continent, such as Europe, or even for the entire globe. Here is an example of our global hydrological model. And for one to do that requires a lot of in-situ data. And as you can see here in the top left figure, these local in-situ data are very much scattered over the globe, and there we have a lot of domains that they are ungauged. But nevertheless, through the evolution of Earth observations, now we are able to use a lot of satellite images, and these are providing us a lot of information both in space and in time at a very fine spatial temporal resolution also. And we have been doing that in our services in order not only to using the data to set up the models, but also using this type of data for evaluating the model, and also in a data simulation mode that allows us to represent the physical processes in a better way. So the service that we have been setting up for eShape is called the Historical Data Availability for Water Quantity and Quality. So this is already in an operational mode at SMHI. You can go to the link here listed on the bottom, and there you can find hydrological variables for water quantity and quality for different domains. This is an example from Europe, but also there is information for the entire globe. And we're not focusing only on stream flow data, which is the traditional variable of interest for hydrologists, but you can go on other type of information, for instance, water temperature, total runoff, phosphorus loads, and inorganic nitrogens, and actually many more hydrometeorological information. The example that I'm giving here in terms of dissemination of the service has to do with this special outlook, and you can make comparison of different river systems over Europe and have a better understanding of how these variables are specially what is the status in a special manner. But also you can find historical information of these variables. You can click in one specific region, the region of interest, and then you could find this time series. And of course, you can download the data or you can subscribe to our service. Here, as a dissemination practice, what we do is to visualize the data as a time series. Here's this red line here, but also you can find you can compare this specific time series of that specific year to the climatology. Like, for instance, what has been the general patterns throughout the years. And that is quite a lot of information for the users also. But talking about the users are interested on putting trust in a specific service. And for us, we are trying to ensure trust and engage with the users by continuously communicating the model performance for different variables. We have been downloading a lot of satellite data, Earth observation data from the DIAS platform, the Copernicus Data and Information Access Services, and we have been evaluating the model variables to these Earth observations. Here is just an example of different variables for actual evapotranspiration, snow information, and also soil moisture. And this is very important because we can tell the users for specific regions if these variables are having good performance or not, and if they should trust the data or not. So we want to be very much transparent when it comes to model performance for the different regions. But nevertheless, as I mentioned at the beginning, the users are operating at the local scale, and therefore we have also kind of like a know-how on how to downscale the information to the scale that the users are operating. And to do that, we are using a very much agile approach where we are co-designing new services for them, we are co-creating that, and we are co-evaluating the service. This is an example here that has to do with the Lake Hume in Australia, where we had our initial large-scale hydrological model set up at a core spatial resolution. But after talking with the users, after engaging with the local users, we are able to redelineate the service, and we are able to recalibrate the service so that we can achieve better model performance. And by doing that, we can ensure their trust. I'm going to give now various of examples of how this historical data have been used from our users. That is an example from an ongoing Horizon 2020 project called Prime Water, where we are engaging with local users in the USA, in Australia, and also in Italy, in Europe, that has to do with different water-dependent industries. And we are providing historical information and also forecast to the users for them to set up a decision support tool and make a better estimation of the status of today and also for the coming 10 days. Another example has to do with the hydropower sector in Sweden, where the industry, the hydropower industry, is very much interested on snow information, and they have been doing a lot of surveys of snow. But nevertheless, we have been downloading fractional snow cover, snow water equivalent, and we have been assimilating these products in a seasonal forecasting service that we have set up. And through this assimilation of the Earth observations, we have significantly improved the seasonal forecasting skill. And by doing that, the hydropower users, they can make a better regulation of the reservoirs, and therefore it can end up to significant added value in terms of economy. The last example here has to do with water security and risk reduction. So one could actually find this historical data, can make assessments of where we had high values of discharge over Europe or low values. That means where we have floods and where we have droughts. And based on that, they can also use satellite data to monitor the situation. This is in a historical mode, but you can do that on a near real-time applications. And when you see that something like a region has high risks of flooding, then you can use products from Copernicus. This is the Copernicus Emergency Management Service, which is called Rapid Mapping, and you can see the regions that they are considered as flooded according to the Earth observations. So for me to conclude here, I only have three very simple take-home messages. First of all, the fact that Earth observations have evolved the water sector, and this is simply because they do provide fine spatial and temporal resolution data. The other has to do with that this Earth observation driven large-scale water services are very much important, because not only they provide an outlook of the hydrological status, but they can allow us to set up new services at different places of the globe. And finally, we need some type of downscaling of these services. We need to customize it, and therefore we are working a lot with local users, understanding their needs and tailor the service in order to add value for these downstream applications. And with that, I would like to thank you all.